My name is Nina Rans. I've been a committee member since 2013, but I mostly hide in the dark corners and very rarely come out to play with real people. I sit in the core group, which is the group that manages first 16 chapters of the standard, which is the part of the standard that talks about the language syntax and doesn't really deal with the library. So I'm one of those people that make sure all the commas are in place and that all the rules are unambiguous and say what they need to say. I obviously also have some sort of a affinity for the letter C, completely unintentional. Why am I here? A lot of people spent lockdown doing all sorts of interesting things like learning a new language and catching up on all the books and all the movies that they haven't seen. I helped my dear friend John Lakos. Oops! We're all good. I helped my good friend John Lakos and a couple of other very, very smart people write a book. I was their pretty much language lawyer. I was there to make sure that everything they write is absolutely and perfectly correct. It was a fun way to spend the lockdown. The book is aimed at people who know C++03 and want to get familiar with the new features that exist in C++11 and 14. So we break down all the features that have been introduced, and then we categorize them based on how easy it is to use them. Safe really means that you're very unlikely to do something wrong. Conditionally safe means that you should be careful about what you do, and unsafe is sort of use it if you really must. We also describe common pitfalls and how to avoid them. I highly recommend it, not just because I helped write it, because it's really a good book. Why 11 and 14? Because writing all the new releases would be a huge thing. I think 17 is coming up at some point, but we haven't started working on it yet. Anyway, as I was doing the research, I noticed that we now have quite a nice collection of types that have special provisions. And I thought it would be nice to just go through them all and see when we need them and why we need them. And the reason we have special types in the standard is because we want to give user-defined types ability to behave like built-in types in certain situations. Sometimes we have new features, and because we have new features, again, we want to define a subset of types for that particular feature to apply. And then, again, we have a few ones that we'll see at the end, which are related to certain common programming patterns that were undefined behavior before, but we now want to make it well-defined, so we're sort of blessing this subset of types to do certain special things that normally you wouldn't be allowed to do. But before we start, I think we should remind ourselves a little bit about the C++ object model. And this is a sentence from the standard. I will be quoting standard a lot because I like the standard. And I can't say anything better than the standard can. So, C++ object model. The constructs in C++ program create, destroy, refer to, access, and manipulate objects. The takeaway from that sentence is you can't have a C++ program without the objects. Objects are just basic building blocks of a C++ program. This is another sentence that's quite relevant for our talk. An object occupies a region of storage in its period of construction throughout its lifetime and its period of destruction. There are a few words there that are quite relevant, which is storage. We're going to be talking about storage. We're talking about lifetime and then certain things that are happening at construction and destruction. Two other definitions. This is a definition of an object representation, which is really all the bits that one object occupies. And then we also talk about a value representation, which is a subset of those bits which represent the value of an object of a certain type. Those two are not usually the same, they're two different things. What types do we have of objects? We have scalar types, which are arithmetic types, enumeration types, pointed to member types, and standard null pointer T, which is a type to ensure null pointer safety. We have objects of user-defined types, or class types. And before anyone pulls me up on this, unions are also defined to be class types in the standard. So we do talk about unions there too. And then we also have arrays. When talking about objects of user-defined types, there are certain things that normally apply to them. Normally they have constructor called. When lifetime begins, normally they have destructor called. They normally have values copied using a copy constructor and a assignment operator. Normally they have some layout, we don't know what it is, and normally the object representation and the value representation that we mentioned earlier on do not match. However, when talking about types here, some or all of those rules do not apply. Right, so let's start. Aggregate types. Aggregate types are not anything new in C++11. We had them in C++98. And if you think of arrays as collections of homogeneous objects, then aggregates are really just a collection of non-homogeneous objects. And we can initialize them just like we can initialize arrays. We can initialize them memory-wise. It's called aggregate initialization, and it's a part of an attempt in C++11 to get a uniform initialization. So we wanted to be able to initialize types of objects of every type with a curly brace initialization or list initialization that was referred to as uniform initialization. It was an excellent idea. Suffice to say is that these days we refer to it as unicorn initialization because it is as pretty as a unicorn and about as real as one. So how can we initialize an aggregate? Here's an aggregate. It has two integers, a char and a long. And then I can, using my list initialization, which is these curly braces, I can provide an initializer for every one of my sub-objects, or I can provide an initializer just for the first one, and then everything else is initialized from empty curly braces. I can even use an object of the same type, and then you get member-wise initialization between the two, which is cool, except if you, at some point, modify what your aggregate contains, your initializers could possibly have a different meaning. So we added designated initializers in C++20, and now you can actually call out which sub-object you want to initialize. So again, I have an aggregate. This time I even have some default initializers. And now I write x1 and I provide an initializer for my C member. This is really cool because now when I add another integer, my initializer doesn't change the meaning. There are a few things to be careful of. One of them is the name lookup. So in my second example, I've initialized B with an A. That's actually not the A of the x2 structure, it's the outside A. And also the initialization of the sub-objects happens in the way that they're declared. So if your order of initializers is the wrong way around, you might get something like I have in the third line where .a is initialized with .b, which doesn't have any value yet, so you get an indeterminate value for a. Most of the compiler writers will warn you about this, but still, when you use designated initializers, just make sure that you initialize them in the order that you have to declare them. The definition of aggregates has changed, and in every single release of the standard, it's a different definition. And this is a nice way of seeing what we do in the standard. We learn and we expand, and we try and get things right, but sometimes we don't. So here's a journey over a definition of an aggregate. Let's start with C++03. So an aggregate is an array or class with no user-declared constructors, no private or protected, meaning all the data members are public. There's no virtual functions, and there's no base classes. Excellent. In comes the 11, and you will notice that we have changed something about the constructors. This is because explicit constructors are a new feature of C++11, but the difference between user-provided and user-declared is that in C++11, you can explicitly default or delete a constructor. So in C++11, we actually allow you a class that has an explicitly deleted or explicitly defaulted constructor is still an aggregate. The last line is brace or equal initializers. It's not actually limiting the scope of the types. It's just because we didn't have brace or equal initializers in C++03, so that didn't actually change anything. And in fact, that's the first thing that we removed in C++14. So now you can provide your default initializers for aggregates, and if you don't have an initializer expression, you pick up your brace or equal initializer. In 17, we added base classes, public base classes. It looks like we fiddled with the constructors, but we actually didn't. The inherited constructors are there because we added base classes when we didn't want to take in the inherited constructors too. How do you initialize your base classes? Well, you initialize your base classes first, and then you initialize your non-static data members. So here's an example of an aggregate that has a base class, and first I initialize my base class with this one, and then I initialize the non-static data members of X. There's something called brace elision, meaning that you don't actually have to provide these two braces around the base class initializer, and you can write 1C21, and it has exactly the same meaning, and you have saved yourself 2 keystrokes. Probably gained a lot of headache, because once you come back to looking at your initializer, it isn't all that clear what you're initializing anymore, but you do you, boo. So yeah, this is the 17, and then the C++20 came. And I'm not sure if you noticed this, that we go back from user provided to user declared, which was the C++03 state. So despite the fact that we have explicitly allowed, defaulted, and deleted destructors, we now taken them away. Why? Because someone brought this to attention. This is a user-declared class. It has a default a constructor, and the user obviously didn't want to have this object of this type default constructed. So if you try to default construct it, your compiler says, no, you can't do that. But if you use aggregate initialization, all is good. Oops. Or an example like this, where we have a value constructor, and the value constructor is explicitly deleted because, for whatever reason, this user didn't want to initialize the type from an integer. And if you try to use the parents initialization, you get a compile error, but if you try to use aggregate initialization, you compile. Oops. So we fixed our rules. There's even a paper that you can look at, P1108, P008, which provides the motivation and then the wording. And it's a nice way of seeing how the committee works. There is a library trait, and it has been added for a specific purpose, which is in place and construct library idioms, where types need to take some parameters and then forward them to another type. They need to use parents initialization for this, because parents initialization and list initialization have different semantics. If you try to use parents with non-aggregate classes, your STD initializer list will be preferred, and that's not really good. However, if you just use parents for aggregates, then you get an error, because you can't. That's a lie. You can't initialize an aggregate with parents initialization, so you would branch on this library trait and do brace initialization for non-aggregates and list initialization for aggregates. Or at least that's what we did. And then someone said, well, I don't actually like that. How about we fix aggregates? How about we add parents initialization for aggregates? And that's what we've done. This is the paper. So now if you try and initialize your aggregate using parents initialization, despite the fact that you don't actually have a constructor that takes that many parameters, you still get member-wise initialization. There are some limitations. Designated initializers are not supported. Narrowing conversions are permitted. I didn't mention this, but if you use list initialization, wherever you use it, you can't have narrowing conversions. But it's allowed here. It's really trying to mimic an initialization of a non-aggregate. You can't use designators. There is different rules for any temporary objects that get created in any of these. Is it working? In any of these initializer expressions, and you can't do the whole brace elision. You have to specify all your braces. So, all those typing that you have to do now. Now that we have this feature, I'm not really sure whether there's any purpose to the STD is aggregate. I mean, the motivation went away. I assume at some point the trait will go away too. Right? One down, and 1, 2, 3, 4, 5, 6, 7 to go. Yay! Standard layout types. I like standard layout types. They have such a good name, and I was trying to describe them in any better way, because standard layout types really have a standard layout. Or another way, they have a predictable layout. And the standard is very explicit about what they're for. They're there for communicating with code written in other programming languages. C. What do they look like? They have the same access control for all non-static data members. And this is because if you look into the standard, the only time we ever talk about the layout of non-static data members is for those that have the same access control. It doesn't matter whether it's public, private, or protected, but if it's the same access control, then we have some rules about how they're laid out. It has all non-static data members and bit fields first declared either in the most derived class or in only one base class. It's a bit of a mouthful, so let's look at what that actually means. We have a structure X here, which is a standard layout. It has no non-static data members, fine. Then we have a structure Y that has some non-static data members first declared in the structure Y. That's fine, and nothing here, good. We have structure Z, no non-static data members, then some in one of the base classes, and none here, again, good. And then if we go to struct Q, that has some non-static data members here, and then some in, oh, I wrote wrong. Oh, that was supposed to be Z. Apologies. Can you all pretend that it says Z here? So if it said Z here, then I would have some non-static data members here and some non-static data members here, and then this is no longer a standard layout. Again, why? Because we never talk about the layout of base classes in between themselves. So if more than one has non-static data members, then again, we can't reason about how they're laid out. Has no base classes that require a distinct address. Now, most of the times, two objects in C++ can't take up a same address, unless one of them is a sub-object of another, or at least one of them is a base class of 0 size, and they are of different types, because two objects of different types can't exist at the same place. We have extended this a little bit in C++20, and now it doesn't say base class, it has a sub-object. And this is because we introduced this cool thing called no unique address, and it's an attribute, which allows that even a non-static data member occupies an address of another one, provided one of them is of 0 size. It's an attribute, so you get what you get. But the thing that take away from this is the whole point of different types. So if two objects are of the same type, there's no way they can be at the same address. So if you look at the structure A, which is a standard layout, fine. Structure B has one base class, fine. C has one base class, fine. And then D has B and C. Both of them have an A base class. And those two base classes can't live at the same address. So this breaks the rule of base classes having a distinct address. And then E has a base class with a class sub-object. And then it also has a non-static data member of A type. And those two things can't live at the same address. So that's not a non-standard layout. That's not a standard layout class. Has no virtual functions and no virtual base classes. Why? Because we don't want to have any virtual tables. And then all base classes and non-static data members follow exactly the same rules, and no reference members because we don't talk about the representation of references in C++. What can we do with that class? Well, as I already said, the layout is really dependent only on the non-static data members. It just follows out from the rules. It has this cool feature that the address of a whole object is the same as the first non-static data member and all of the base classes. So you can do this pointer interconvertibility between the base classes, the first non-static data object and the outside object. And you can use offset off. Now, offset off is well defined with standard layout class types, but it is conditionally supported with non-standard layout types. So your compiler will probably let you do offset off even on non-standard layout classes, just such code is not portable. There is something else that's quite cool about standard layout types. It's the notion of common initial sequence, which is when you declare your non-static data members, if they have a layout compatible type, which is actually the same underlying type. If they match those types in the declaration order, then that's a common initial sequence between the two types of standard layout. And what you can do with that, also, now that we added no unique address, either both of them need to have it or neither do because it's an attribute, so it might or might not work. So what can you do? You can put them in a union, and then you can read a common initial sequence between an active and an inactive member, meaning if you have an active member and it shares a common initial sequence with an inactive member, you can come through the inactive member and read that common initial sequence. There is a restriction that the read must happen through the union object and not through a pointer or reference to the inactive member. Let's see what that looks like. I have two structures here, structure A and structure B. They share a common initial sequence in that integer. And then I put them in a union. I make A the active member, and then if I read through integer of B, that's fine. But if I try to read a character, that's undefined behavior. And this looks a bit, but if I plug in some nicer names, this might be more obvious what I'm doing. So if I put my type ID as the common initial sequence, I can check the type ID through any of the union members that share the common initial sequence, and then I can do something based on the type ID. Again, like I said, the read needs to come through the union rather than doing something like this where I bind a reference to the inactive member and then I read through that. This can break aliasing and you can get something that you don't want to get. So just read through the union. There is a library trait, STD Standard Layout. It's been introduced in C++11. I have tried to come up with some uses for it, and I honestly couldn't. If anyone knows of any, I would gladly know. I also tried to write some code samples and then assert on STD Standard Layout, and I found quite a few bugs which would suggest that it isn't widely used, because compilers do actually fix bugs that you report to them and that they think are widely used because they're nice people. So yes, you have that library trait. What you do with them, I don't know. There was a question at the fireside chat, which was we should somehow note things in the standard that are useful and things that are not useful. And Daisy said something that was really cool, which is things that are useful to one person are not necessarily useful to another. So it's very difficult to determine what is useful and not useful in the standard. But this is not useful. I didn't say that. Anyway, right, trivially copyable types. Before we go there, we need to remind ourselves about trivial special member functions. We'll start with a default constructor. It's not user-provided, meaning the user didn't want anything special to happen with this type. It has no virtual functions and no virtual base classes, which really means there's no virtual tables. All the base classes and non-static data members have trivial default constructors, which just means everything that is the sub-object of this object also doesn't need to do anything on construction. And there are no default member initializers for non-static data members. In other words, a trivial default constructor does nothing. It's a no-op. We have a trivial copy constructor and an assignment operator. Now it says copy, but whenever I say copy, I actually also mean copy or move. So it's copy or move constructor or copy and move assignment operator. And again, it's not user provided. The class has no virtual functions, no virtual base classes. All the base classes have a yada, yada, yada. Same rules apply. Trivial destructor, same, not user provided, not virtual, and destructors of all base classes and non-static data members are trivial. Again, for such a destructor, when the object gets destroyed, the compiler doesn't need to do anything, even if you do invoke a destructor or if a destructor gets implicitly invoked. So what is a trivially copyable type? It is a type that has at least one non-deleted copy operation, meaning there is at least one way that we can copy this object, either through assignment or through copying. In C++20, we modified this definition to take constraints into account too. So we talk about not just non-deleted, but also most constrained copy operation. All the copy operations it has are trivial, and it has a trivial non-deleted destructor. Now, this might come as a surprise. But if you think about it, a copy operation can be one of two things. It can either be assigning a value from one type to another one, or it can be seen as destroying one object and then copy constructing it from your source. And for that case, you do care about the destructor. So destructor is there. It needs to be non-deleted. There's something missing. There are no requirements on access control and ambiguity of call. There's also no requirements on which copy operation is non-deleted. And this will become important later on. So what are the implications? the value is contained in the underlying byte representation. So when we spoke about object representation and value representation earlier on, for a trivially copyable type, your object representation is your value representation. So if you take bits of your type and you just blast it into another object, your type will have exactly the same value. And that's exactly what you can do. You can mem copy between objects of such type, and you can copy it into an array of char, which is really a way of representing it as object representation, and back into the object of the same type, and again, you get the same value. Cool. Not only that, compiler can do that. So a compiler can see that your object is trivially copyable, and they just not bother with the copy constructors in the sum. It just does the same sort of bit blasting around. There's a trait. This is actually a useful trait. It's introduced in C++11. If your object doesn't satisfy is trivially copyable and you do something like memcopy, it's undefined behavior, so make sure you check for that. What it doesn't ensure is that your object actually wants to be copied in the context that you're doing the memcopy. So if you're writing something like this, well, first of all, don't, because this is bad. But if you're trying to do something like this, I have a structure X, and that structure is only move constructible deliberately. However, I have here a copy function that takes a destination and a source and then does the memcopy, and it even checks for is trivially copyable, so there's no undefined behavior. But the question is that really okay? Because whoever wrote this class only wanted move construction to happen, and that there is a copy from an L value, so that's probably not what the user wanted. So you probably you don't want to check just for the is trivially copyable, you also want to check for either is copy constructible or is move constructible, whatever is relevant for that context. Trivial types. It amuses me, because trivially copyable types are so useful, and then you come to trivial types. I'm not really sure what I can say. Trivial types have come in as a definition because we had to talk about types that existed in C++03. So a trivial type is a type that is trivially copyable and also trivially default constructible. That's it. What can you use it for? Nothing. We had it in the standard to describe certain situations, but as a user, again, this is one of those things that you just ignore. You know that it exists, but you'll never need to use it. There's a trait. I don't know what to say about this trait. It's probably as useful as is standard layout. You can make a check for whether your type is plain old data, which we'll come to next, but other than that, there's nothing that trivial types have that's special to them. You either want to talk about trivial constructability, which you can check with the traits, or you want to talk about trivial copy construction, again, which you have a trait, but a trivial, it's not very useful. And with that, we move on to pod types. I have a nightmare of pod types. The pod chapter of the book took about 2 months to complete because there's so many rules that have changed and evolved that it took so long to write correctly. But anyway, what are pod types? We defined them in C++98 for C compatibility. And it's really a set of types whose physical representation mimics that of C type, and also that behave like C types at construction, destruction, and copying. But as we mentioned before, the physical representation can be used in certain useful ways without needing the whole construction, copying, and destruction part. And we can use the trivial copyability without actually caring about standard layout things. So in order to do better, in C++, oh, yeah, this is the original definition. We don't have much to say about that. In C++11, we decided to split those two properties. So the properties relevant to object layout became standard layout types, and then for those you get the benefits that we already spoke about. And properties relevant to object construction, copying, and destruction became trivial types. Although, again, it's not really trivial types, it was the trivial copyable types that we cared about, because that's where you get the benefits for the trivial types, is just to cover the whole subset of a C++03 definition. And that just meant that the original term was no longer needed. Now we have a different way of describing pod types. We removed the term, then we deprecated it first, and then we removed it in C++20. So instead of talking about pods, we now talk about trivial standard layout types. And there's a little bit of a demo. So this is a strings library from the standard. It used to say pod type, and now it says trivial standard layout. So it made the standard slightly simpler. I think this goes back again to the fireside chat. Somebody asked, what is it that what did you like deleting? This is one of those things that's just satisfying. You know, it makes everything slightly simpler. You don't need to maintain several definitions. There's a library trait. It's introduced in C++11. It's deprecated in C++20, what you can do with it. You can check whether your type is usable with certain parts of the library, but that's about all that you can do with it. Literal types. Literal types came in with the move to compile time evaluation. There's a whole move towards expanding what can be done at compile time with a view of possibly even, well, not possibly, but with a view of implementing the whole of reflection using these const expr constructs. So as we started talking about what objects you can create at compile time, we needed to have a definition for those types, and this is where literal types come in. So a literal type is one which an object of which you can create at compile time. Can, but you're not guaranteed to be able to do so. So there is a way of creating them at compile time, but not all possible creations are available at compile time, and also there's no guarantee that you can invoke, that you can use that object at compile time. There's just a guarantee that there is a way for you to create it somehow. The standard doesn't really talk about compile time. The standard talks about constant expressions. So whenever I say constant expression, you think compile time. We pretend that the compilers don't exist. So what is a constant expression? It's a requirement for constant initialization. We usually talk about constant initialization because everything that happens at compile time needs to be triggered somehow. And it's usually triggered by creation of an object. So it's usually in the context of some initialization somewhere. And we have some new keywords. We have const expr, which was the first one to be introduced. You have const expr functions, which can be invoked at compile time, but don't necessarily have to be invoked at compile time. And you have const expr variables that are initialized at compile time, but they're also constant. So you can't change the value once you create them. And we realized that there's a few things missing for that. So we added const-eval, which applies to functions. And const-eval functions can only be evaluated at compile time, meaning at runtime they're not even available, you can't get to them. And then we have const-init, which applies to variables, and such variables are initialized at compile time, but then you can also modify them. We do have limitations to constant expressions, and I thought whether to talk about this or not. But it's very difficult to list everything that's possible at compile time. It's more of a question of what you can't do at compile time. And even that set is getting smaller and smaller as compilers get more and more experience. But it's sets of two things. It's things that are simply not possible or correct at compile time, which is all sorts of locale things and other things. And then things that are simply difficult to implement at the moment. There is a very good talk by David, who is one of the key person in this whole reflection and compile time evaluation thing. So he talks about things that you can and cannot do at compile time and where the compilers might go in the future. He also mentions something that's very interesting, which is when you move your evaluations to compile time, it saves you runtime, but you also don't get the optimizations that you get at runtime. So he has this nice demo where he shows that as soon as you make your classes slightly more complex, compile time increases quite a lot. And to understand why that happens, I recommend the paper by Andrew Sutton that explains what it is that you can and cannot do at compile time and why. Why do you get what you get? So these are the literal types, or the things that you can create at compile time. You may find this void interesting. It's there because the original requirement on const expr functions was they return. Am I still? Oh, yeah. Has to return a literal type, which meant void const expert functions were not allowed. And the reason you would have a void const expert function is just because you went through your code and you plastered const expert wherever you could, and you simply, one of those invoked a function that returned nothing. So we made void a literal type. But what we really care about is these literal class types and what they look like. So here we have that aggregate type again, or a type that has at least one const expert constructor that is not a copy or a move constructor, meaning there must be some way of creating this thing at compile time. In C++ 17, we also added lambdas to the list. Closure type, which is added there, is really lambdas. That's another way we refer to lambdas in the standard. What it also says, every constructor call and all the brace or equal initializers need to be constant expressions. All of the parts of that type need to be literal types, and it needs to have a true or destructor. In C++ 20, we did two changes. We changed the trivial destructor to const expert destructor. This is because now in C++ 20, your destructors can actually have a body. And as long as that's a constant expression, you're fine. We also removed this requirement. It looks like we removed it, but if you think about it, it's not actually needed. Because if you're talking about a const expert constructor, everything that the constructor invokes needs to be const expert, and therefore every constructor call and full expression just falls into the first rule, and you don't actually have to write it out. It's understood. We have a trait, a poor little trait, that was introduced in C++ 11, deprecated in C++ 17, and removed in C++ 20. It didn't have a long life. And the reason for that is something that I just earlier mentioned, because the question isn't whether your type can be constructed at compile time. It's whether this particular construction can happen at compile time. So that's what you need to be asking yourself. And it's the same thing when we specify something. We don't have to specify that this type has to have a way of being created at compile time. What we have to say is, when you create it like this, it has to be a constant expression. So yeah, you don't need the trait. And what I mean by that, like we have a structure here, which is of literal type, and I can default construct it at compile time, but I can't value initialize it at compile time. That's really what it means. So really what I want to be asking is my constructor that I invoke to initialize constant expression or not? That's what I care about. And talking to a few people, I'm not even sure that we need a definition of literal type. It is possible that just like we hooked in that rule for the sub-object initialization into the whole constructor needs to be a constant expression, it is possible that we can simply remove the definition on literal type at some point and just express it through the rules of constant initialization. And so we come to structural types, which are related. So when talking about non-type template parameters, we had certain limitations to what we could put there. We couldn't put any types, and that was quite unfortunate, because why? There are user-defined types that we can create in compile time now, so why not have non-type template parameters to define type? And that's exactly what we did. So we defined structural types, which can now be non-type template parameters, those usual things, and then also literal class types that have all of its sub-objects public and non-mutable and of structural type. And you might wonder why, and the answer is because you need to have some way of knowing whether you already have a certain instantiation of a template. So you need to have some way of comparing the objects of two type, but the equality operator isn't really the right answer there, because not only do you have to know whether these two things are the same, you also need to be able to look it up. So what the compiler actually does, it creates a hash of all the public non-static data members, and then it hooks it into a table, and then you can look it up based on this hash. This is a fairly limited definition. There are papers coming to expand it. Again, I don't see whether Barry's here. Is Barry here? No? Anyway, there are a few people writing a proposal to expand this to sort of allow for some way of specifying even classes that have non-public data members or which are mutable to be able to work with non-type template parameters. Watch this space. And we come to the last one. Ooh, 18 members, excellent. We'll get through this. Stay strong. Implicit lifetime types. So before we go there, again, a little bit of a reminder about what object lifetime is. Again, a quote from the standard. An object is created by a definition, a new expression when implicitly changing the active member of a union or when a temporary object is created. Excellent. And then we have some code, a very common code. We malloc some memory, and then we initialize it because we're good people and we always initialize everything that needs to be initialized, and we return it and we think we're fine. Do I have a typo? No, okay. But then I look into my definition and there is no definition there. There's no new expression. There's no union or a temporary object, so that's undefined behavior. Yeah. Yes. Oh, you have this case. I malloc some array, and I just calculate where the end is. I don't even use this array. I'm just doing some pointer arithmetic there, and then I go to the standard and I look at when is that pointer arithmetic well defined. Well, it's defined if one of those is a null pointer, which it isn't. It's well defined if there's an array object, which there isn't, because there's no new expression, there's no changing of the union, there's no all those things, which I can't remember now. So we fall into the last one, which is this behavior is undefined. And this is STD vector. Now, this is something that Bjarne said during this week. He said, not everything that's undefined behavior means that the compiler won't do something that's well-defined. And this is one of those cases, because now compiler will actually optimize against this. Because why would they? If they did something with this, you'd break vector, and you pretty much break the whole world. So this has to work. So people went about fixing it. Not because it would ever break, but because we just wanted to plug the standard and make it well-defined. Like, we are slightly obsessive people. So we looked into those types and we reasoned about what those types are. And it's usually types that come from C. So they have a trivial constructor, they have a trivial destructor. So we made a subset of types that get this special pop-up into existence when they're needed set. And we created implicit lifetime types, which are scalar types, array types. And when we talk about array objects, we don't necessarily talk about the sub-objects of an array, but just the array itself. Because you can have an array with all the things dead inside. And then aggregate classes and classes with a trivial destructor and at least one trivial constructor. Now, if you look very carefully, you will notice that we're not talking about destructors of aggregate classes. And again, this is just to demonstrate how a committee works. There is a whole discussion on whether this is a good enough definition or whether we need to say something about destructors of aggregate classes when it comes to implicit lifetime. But this is the current definition, either way. And then once we had this implicit lifetime rules, we had to fix our object lifetime. So this is how it looked before. And then we also said you can start in lifetime by an operation that implicitly creates objects. Cool. Then we had to do a few other things. We had to specify what those operations are. And this is the list of operations that implicitly creates object. And we also did a bit of a fix around the arrays where we said that if you create an array of chars and all these other things, then you have also implicitly created object within the region of the storage occupied by that array. So now both of those examples work, which is really cool. There is no trait for that. And the reason there is no trait is this is not meant to be used deliberately. You're not meant to go away and try to make your types implicit lifetime and then do some special funky things with them. You just if you have to write code that I have demonstrated, you probably already have that code. Try not to write new one. Because if you're, but the reason for that is because these implicit lifetime types are trivially constructible and trivially destructible. If you just use them in the way that C++ is designed to use the objects, your compiler will optimize around the constructors and destructors anyway. And if you at some point add constructors and destructors, then it will reason about it and do the right thing. But yeah, it's just there to plug a hole. Ooh, excellent. And we got to the summary. So this is the list of all the types that we have discussed in this talk. I've put all the traits that are relevant to it, and I've put when do you care. But I hope that you have taken some of the hints that some of these things you will never care about. Some of these things you should know exist, and then geek out with your friends how you know the rules. But what you really care about is standard layout type. You care about trivially copyable types. You care about literal and structural types in the sense that you need to understand what it is that you need to do in order to either get compile-time initialization or put things in a non-type template parameter. And if you want to make use of the nice aggregate initialization, I guess you also need to understand the aggregate type. But trivial type and implicit lifetime type is really there just to geek out. And on that note, we end. All right, any questions?
I've got a question. Do you happen to know these type traits, can they be implemented in C++?
Well, you get the library. I think there are some of them are specified. I think Marshall would be better chance of this. I think some of them you can't actually specialize. You're not allowed to specialize.
Some of them are implemented by a compiler.
Yes. You get them in the library.
Okay, so you have to stub them out in the library.
Yes, some of them need to be implemented by a compiler intrinsically. Like you cannot implement them in library itself without the compiler providing the support for them.
Okay.
Hello.
Hello. Thank you for the talk. I'm not really sure I agree with your assessment of those traits, specifically standard layout and implicit lifetime. For example, standard layout you mentioned is useful for interoperating with C and other languages. So it might be reasonable that you want to make sure with a static assert, as you had on the slide, that something like that happens. So I see value in that. And the other thing is you also want to make sure that nobody mistakenly changes that and you don't notice it. So having the static assert there makes sense. And I want to make a similar argument for the implicit lifetime. I was at a great talk by Robert Leahy a few days ago, and he showed a use case where they want to make sure that they are able to efficiently transmute bytes from and to objects to a very high-speed performance database system. And they were using, let's say, functions that rely on some type being implicit lifetime, but they couldn't really assert it. So I think it would be actually valuable to have that trait just to make sure that in your system something works. I was actually talking to Timur, and we were proposing to actually write a paper for that. But you seem like you disagree on this, so I wanted to know your thought about that.
I don't disagree. I think what I was trying to say, when we were talking about is aggregate type, you can actually make, you can branch your code based on whether something is standard layout and do something else if it isn't. Aggregates. Or it's the same thing with trivially copyable. You do one thing if it's trivially copyable and something else if it's not. You can't really do that for standard layout, and you can't really do that for implicit lifetime. It works or it doesn't work. But you're right. If you have an assertion just to make sure that your code is working correct, that's definitely one of the use cases.
Okay, so when you're talking about usefulness, maybe you refer on branching on it, but for sanity check, it will make sense to have it.
It does make sense.
Okay, thank you.
Yes, you're right.
Hi, thank you for the talk. One thing that I find aggravating about a standard layout is that many times I wanted to invoke offset off, but because it is a macro, it doesn't work with templates. So why doesn't it work in templates? Do you know?
As Marshall says, templates are not types. It has to be a type. So you have to have a...
Sure, but I mean a fully instantiated template, okay? The macro offset off doesn't work with fully instantiated templates.
It does not.
Should if it's a standard layout.
Yeah. Can we look at the sample code after this, and I can give a better answer. Inigo will help you out.
I'll let Nina help.
Thank you very much.
Let's talk about that. Yeah, let's see an example after this, and we'll see what's happening.
Yeah. Thank you very much for the talk. I found it very useful. You mentioned about the, what is it, no unique address attribute.
Yes.
And you pointed out that if you have two data members that are adjacent to each other that are of the same type.
No. So before the only time you could make use of something that's zero size is if it was a base class, and then it could actually not take up any space. But if it was a non-static data member and it still had no data members, it had to occupy some space. But if you annotated either that or next to it with a no unique address, then the compiler can sort of flatten the layout of such type.
Okay.
Does
Thank
that
you.
answer your question?
It sounds like I misunderstood, but I'll check and I will. And if I have a follow-up, I'll catch you some other time.
Okay.
Thank you.
Oh dear.
I'll give you an example of where has no unique address is really, really nice. Most allocators have no actual state. Std allocator, for example, has no actual state. Every container in the standard library has an allocator. Every allocator where container, except for array. Okay? Every single one of them has an allocator. If your standard library implementation had to store an allocator, that's on a 64-bit system, that's 8 bytes on every container. That is just wasted space. And so if you have, if you have an allocator that has no state, and you can use has no unique address, or various hacky tricks that everybody used before C++ 17, you don't have to actually take up 8 bytes to store nothing in every vector, every list, every deck, every queue, every stack. So it's a big deal when you're trying to write components, because those get used a lot. So I just wanted to say that thank you for the presentation. It's very nice. I wanted to say I also saw a presentation earlier this week on the implicit layout types or implicit lifetime types. It was Monday. I think it was in this room. It was very good. So, I'm sorry? Robert Leahy, thank you. So anybody who is really interested in implicit layout types, all the nuts and bolts, that's a good talk to go to.
Thank you.
Thank you.
There is one question from an online participant.
Okay.
It's about STD launder. So the question is, yeah. So
Launder, right.
yeah, the question is, do we have any need in STD launder for implicit lifetime types?
Marshall, yeah, please.
Robert Leahy talked about this on Monday.
And what is the answer?
Yes.
Can you please elaborate?
So again, Robert Leahy spoke about this on Monday in his talk, and he had an example where it was necessary to use launder.
Okay.
I guess watch his talk. Is that it? We're done? Pablo's just trolling me there. Right. Thank you. Yeah. Start launder Pablo. Right. Thank you very much.